Welcome back, everybody. Having finished an overview of the proof of semi-stable modularity and Fermat's last theorem, we're now going to go into chapter 3 of my notes, which is the first of many chapters seeking to fill in gaps found in those proofs. We're going to start today by talking about modular functions. Okay, this chapter, though, in general, seeks to explain various concepts needed to fully grasp modular forms, the fivefold theorem, modular curves as algebraic curves over Q, Hecke operators, new forms of abelian varieties, Eichler-Shimura, modularity in terms of L functions and isogenies, all kinds of great stuff. Okay, let's start out. So we're going to first just today review the basics of modular functions by looking at the definition. We're going to look at a congruent subgroup big gamma of S equals SL2Z. Remember, a congruent subgroup is just a subgroup of SL2Z that contains gamma 0 of n, gamma 1 of n, or gamma of n for some n. I defined gamma 0 of n, gamma 1 of n, and gamma n in a previous video. Also, please see my series of talks on the congruent number problem for more information. Let's let H be the upper half plane and the complex plane. Let's let GL2 plus of R be the group of 2x2 matrices with real entries and positive determinant. There is an action of GL2 plus of R on H by what we call fractional linear transformation. If I give you a little gamma in GL2 plus of R with entries A, B, C, D, and a Z and H, the action is given by gamma Z equals AZ plus B over CZ plus D. So this is what we call a fractional linear transformation. What's a modular function? If I give you a function f on the upper half plane H, let's define f composed gamma, where gamma is in GL2R plus, as a new function given by z maps to f of gamma z. So it's the function f evaluated at az plus b over cz plus d, in other words. Let's let big gamma be a subgroup of S of finite index. A modular function for big gamma is a meromorphic function f on H, which is invariant under composition by little gamma for all little gamma and big gamma, and such that given delta in S, if we find a natural number big M such that f composed delta of z plus n equals f composed delta of z, so we've got an additive periodicity with period m for all of the functions f composed delta for all delta in SL2z, in other words. And by the way, such an M exists because big gamma is a finite index in S. Then if we let big F be the meromorphic function on the punctured unit disk d star in the variable q equals e to the 2 pi I z, defined by f of delta z equals big F of q to the 1 over m for z and h, then we want to require that this big F here extends to a meromorphic function on the full unit disk d. So we extend through the origin to a meromorphic function on the full unit disk. So what's going on here is you can map the upper half plane to the unit disk by the exponential map, and we want this additive periodicity with period m to translate to a kind of multiplicative periodicity with period m. Okay. In fact, you can very easily check that these two things are compatible with each other. This additive periodicity in m up here, and this q to the 1 over m power down here. I'll leave that as an exercise. Okay, so we have two conditions we need to satisfy for a function on the upper half plane to be a modular function. This first one's very easy to understand. The second one's a bit of a mess. There's another way of thinking about this second condition, though. So let's look at condition 2 from another perspective. Condition 2 is equivalent to the requirement that for every delta in SL2Z, f composed delta is given by a certain kind of Fourier expansion. It's a sum over n bigger than or equal to some integer n0 of a of n's times q to the n over big M's for mz large, at least for the imaginary part of z large, and for some n naught in z, n naught could even be a negative integer. Now, this is a little bit easier to think about. We're requiring that our f composed deltas have certain Fourier expansions in Q, in other words. Okay. Now, this becomes even easier if big gamma is just SL2Z, because then by condition 1, f composed delta is just f for all delta ns. And so to check that condition 2 is satisfied, we just need to check that this Fourier expansion condition is satisfied for f itself rather than for all of the f composed deltas. Okay, so again, if big gamma is just SL2Z, then condition 2 just means f has a Fourier expansion that looks like this for some m and for some n naught. And these coefficients can be whatever. Okay, let's get elliptic curves involved here. Recall, so every complex elliptic curve E, so every elliptic curve over the complex numbers, satisfies E is isomorphic to C mod L for some complex lattice L, okay? And vice versa, actually. If I give you a complex lattice, it admits an elliptic curve over the complex numbers. I talk about this in a little bit more detail in my series of talks on the congruent number problem, but I'll say a little bit more here. For Z and H, let's let L sub Z be the lattice in the upper half plane generated by 1 in Z. We can work with these normalized lattices, L sub Z for Z and H, instead of arbitrary complex lattices, because the point is, any complex lattice is homothetic to one of these, meaning it's a complex scalar multiple of one of these for some Z and H. And well, who cares if two lattices are homothetic? Well, two elliptic curves over C are C isomorphic if and only if their corresponding lattices under this identification up here are homothetic. Okay, so we might as well work with the easiest, nicest lattices in the upper half plane that we can get our hands on, because they'll correspond to the same elliptic curves over C that any other lattice would. In fact, a precise way of saying this is C isomorphism classes of elliptic curves over C are in bijection with homothety classes of complex lattices. And you can see Silverman 2 for a discussion on this. Why bring up elliptic curves, though, in the context of modular functions? Well, let's let M of S be the vector space of modular functions for S. It turns out this is generated by the J invariant J viewed as a function of Z and H. What's going on here? Well, okay, that function is J of Z equals 1728 times G2 cubed over G2 cubed minus 27G3 squared, where G2Z is 60 times this sum over the lattice over non-zero points of the lattice, omega of omega to the negative fourth, and G2 of Z similarly is 140 times a certain sum over non-zero points omega of the lattice of omega to the negative sixth. Now these G2 of Z's and G3 of, oh, this should say G3 of Z, excuse me. These converge absolutely and uniformly in compact subsets, so they're actually meromorphic functions on H. And what's going on here is you can check immediately, because I gave you the formula for the J invariant of an elliptic curve over C, that J of Z, this ugly function here, is nothing but the J invariant of the elliptic curve y squared equals 4x cubed minus G2 of Zx minus G3 of Z, admitted by the lattice LZ via the Weierstrass phi function. In other words, under the identification I gave you above of complex elliptic curves with lattices L sub Z. Okay? And so I guess what you could say here is, you could say M of S is just C adjoin J. The J invariant kind of governs the space of modular functions for SL2Z. Next time we'll get into modular forms. And so I'll see you then. Thanks for watching.